Okay. Um, so the new stuff that we're covering is starting to get into some aspects of the bonding character between the atoms and what that has to do with the chemical, electrical, thermal, and optical properties, because those are all determined by the electron structure, the electronic structure of the atoms themselves. There's a whole lot to that. These electrons have a specific behavior that is both wave-like and particle-like or particulate, and the two wavelengths and characters of these things are because electrons are in orbitals, and there are some other aspects as well. Um, yes, the dates will be updated from 23. I have to go in and change those, but I can't do those now, and also do all the other fixes and things that this lesson requires. So I will get to that later today so that you guys can actually submit those. This is part of trying to unmess the disaster. So yes, I'm aware that those are 2023 dates. I can't update those for a little bit yet. All right. So the wave-like and particle-like duality of this behavior has to do with the wave-like characteristics being a function of the electrons are in orbitals, and they are defined by probability, meaning a statistical likelihood of being able to find the electron in this given spatial region around the proximity of an atomic core or nucleus. Each orbital has a discrete energy level determined by quantum numbers. So these quantum numbers have some specific designations. The N is the energy level shell. Within those, there are subsidiary levels. There is a magnetic component and a spin component. So you have a spin, you have a half spin addition, and that has to do with whether it's a spin up or spin down. And that pairing of spin up and spin down balance out each other's interactions. So these electrons are free to spin. This is trying to account for all of the degrees of freedom of these small particulates in their orbital pattern. So you have the principal levels, you have KLMNO, and you have 1, 2, 3, 4, etc. SPDF are subsidiary orbitals, so you guys have been familiarized by hook or by crook with the SPDF orbital combinations. We're not going to spend lots of time on those. The magnetic, you really haven't gotten into. The magnetic character and the spin up or spin down relative to the magnetic character is also important for the macro scale behavior of certain materials. That component determines part of why ferromagnetic materials are magnetically responsive. So why does a magnet stick to steel? Ultimately, it comes down to the magnetic character of those individual atoms and the bonds in between them that establishes that magnetic character. The energy states have these regions. So the K shell is n equal 1. The L shell is n equal 2. The M shell is n equal 3. The N shell is n equal 4. So 1s, 2s, 2p, 3s, 3p, 4s, then 3d orbital, then 4p, then 4d. Each of these are representative energy levels that are in order of increasing overall energy. These come from some rather complex derivations going through statistical mechanics. There's an awful lot behind this. We're not going to get into the behind the scenes there. But by having these discrete energy levels, we can see what the interactions are like, and how those behaviors look and what they do effectively. So there's a few things at play here all at the same time. Things that we need to be paying attention to are the fact that the electrons want to occupy the lowest energy states that are available. So it wants to fill up the 1s first, then the 2s, then the 2p, then the 3s, then the 3p. It doesn't want to just have something hanging out in the 4D because that requires expenditure of much additional energy. Unless there is a lot of energy being stored in that molecule, i.e. that molecule is at just an elevated temperature, and all of that energy has to be held by the material somehow, that's where this comes into play. So broadly speaking, as you elevate the temperature, by which we mean really just the kinetic velocity of those individual atoms, and their collisions become more severe and more aggressive and higher energy, that's where these higher states start getting filled and occupied. There's some other kinds of things with radiation and other mechanisms we won't get into because this one isn't a nuclear class, but there's all sorts of different things that can elevate what energy levels are filled and pull electrons up out of the 1s and 2s and 2p orbitals. But it's not the natural default state, and therefore statistically unlikely for us to find many atoms that are actually in those states. So hydrogen, atomic element 1. That means it has a 1s1 configuration. Helium, atomic number 2, has a stable 1s2, meaning that the s orbital is full, it has a spin up and a spin down electron, it's occupied, it's content. So it doesn't want to react. Then you get to lithium, totally different story. 1s2, 2s1, meaning one orbital is filled at 2s1. It wants desperately to either get rid of that 2s1 or to gain a 2s2 and be more like beryllium, to be more stable. Boron, same deal, is 1 in the 2p, so 2p1. Carbon is 2p2, meaning it has 2, 2, and 2 in those 3 levels. That's part of the reason why carbon can react so readily with a lot of other materials. And then getting up to neon at 10 is 1s2, 2s2, 2p6. So 2p sucks up a lot of those other electrons because each of these levels needs to be happy or content or filled is the correct term there. All of those things meaning something very similar in terms of the character of the atoms. They want a spin up and a spin down in each of those bars or each of those slots, you could think of them as. Molecules don't like to have empty slots for any reason. Also, people that have significant gambling addictions don't like to have empty slots, as I'm told. So there should be some things available in terms of the posting. Yeah, we'll try and get there in terms of slides. I'll see what we can do about those. Yeah, one step at a time. So we get farther up the periodic table as far as argon. Neon at 10 is 1s2, 2s2, 2p6. So that looks like this. Yeah, let me do pen just to represent that. So neon is 1s2, like this, 2s2, one spin up, one spin down, 2p6, meaning one spin up, one spin down, one spin up, one spin down, one spin up, one spin down. So all of these slots are filled in the case of neon. I realize that's the greatest way you've ever seen neon drawn. You'll just have to cope with my drawing brilliance for a couple of weeks. So neon is content. Similarly, we have argon, which takes that a step farther, and that is 3s2, 3p6. So argon fills this next energy level. I'm going to do that in black. So argon is everything from neon plus a spin up and a spin down and a spin up and a spin down and a spin up and a spin down and a spin up and a spin down. So each of these represents the electrons and what they're doing. And this is argon. So these are content because they don't really need anything from any other atom. You can make them react still, but you have to go to extremes in order to make that happen. So you have to go to extreme temperatures and pressures. And krypton goes all the way up to the top of our chart there at 4p, with 6 being filled, and those are all stable. So things that are unstable fundamentally have the valence, the outer shell, not completely filled, and this is part of why the reactions can take place. The valence electrons are where all of the business of chemistry happens for the most part. Those unfilled electron shells mean that they either want to get rid of an electron if they've only got one or two, or they want to grab electrons like a playground thug and take them from everybody else. It's just what the molecules do. It has to do with energy minimization of those energy wells at each of those energy levels and optimizing what the energy level is. So it's not actually that the atoms are mean to each other. This is just a governing law of how things behaved. If there wasn't a governing law and the universe was actually ruled by chaos, none of this crap would work at all, and materials wouldn't hold up. All of the particles wouldn't stay together, and life would be absolutely disastrous. So the notion that things are actually, in fact, ruled by chaos is preposterous on the face of it. Deeper studies of chemistry will demonstrate to you very clearly why. So those valence electrons are the most available since they're on the outside. They're the easiest to be participating in bonds, and they control the diversity of chemical properties that these atoms have. So taking a look at something like carbon, atomic number 6, 1s2, 2s2, 2p2, means that when we go back to our energy levels here and we erase and we start over, 1s1, 1s2, 2p2, 2p2 looks like this for carbon. So 6 electrons. That means that it says, hey, I need 4 more electrons to be content. So I need to share a bond with 4 other things, and that may be a different color. So maybe we've got a couple hydrogens that we'll say are yellow. So CH2, and maybe we'll have an oxygen or something like that that wants to give 2, and we'll do that in red because oxygen is often represented in chemistry as being red. And this would allow for a fully filled valence shell if it had a double bond to the oxygen. So we would represent that as C, H, H, double bond to O. So that would be a content carbon. 2 bonds with a hydrogen, 1 electron shared each, and 2 electrons shared between it and an oxygen. This is why this is important, is all because of these energy levels. So that's what this is representing. The valence electrons are the 2s2 and 2p2 electrons. So iron, atomic number 26. Oh, good, they filled it out. You don't have to deal with my terrible drawing skills this time. Great. So this is typically how the energy levels are filled. So you start with a spin up to fill all the cases, and then you start filling in the spin downs. And that's why iron, like carbon, wants to have an additional 4 bonds, the way that these work. So in order to do this, this is a 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. The 3d6 and 4s2s are the valence electrons because those are the outer shells. So the periodic table tells us something about atoms by grouping them into families. These families are these columns. And what that tells us is the far left column wants to give up 1 electron. So why do we use lithium in our batteries? Probably because lithium is desperate to give up an electron and be more like helium, because that's its easiest way to be like the inert gas. That's the one it's closest to. So sodium desperately wants to give up 1 electron and be more like neon at 10. This is why sodium makes so many different salts. Potassium, rubidium, cesium, francium, all in that first column are wanting to give up 1 electron in order to be like its neighbor. The oddball there is hydrogen, because it would rather have no electrons at all rather than try and steal another one just because of its character. So it is always electron donating, leaving it as the key component for acidic behaviors. And without that specific characteristic, without hydrogen being the oddball wanting to give away its one and only electron, literally biological life doesn't happen. So if all of these molecules didn't behave exactly as they do, nothing would work the way that it does at present. So these rules are actually exceptionally important to be able to govern the interaction of materials, whether it's biological, whether it's mechanical, whether it's electrical, it just doesn't matter. The fundamentals are the fundamentals. So we're also in the 2A, you have 2 electrons that they want to give up, and 3B, you have 3 electrons that they want to give up. That includes a lot of these rare earth series and a lot of the actinides, so that's a whole table that gets sort of inserted there in the middle. Some kind of strange stuff that happens in there. But the 2 family, strontium, barium, magnesium, there's a lot of times we're using magnesium salts, calcium salts for different things, a lot of biological importance for those. Strontium a little less so, but barium is sometimes used, different barium salts and things for some metal processing. There's a few others that are in there. Yttrium is used in group 3B for certain kinds of ceramics. At the far right side, you have a few things that are non-metals. Most of the things on the left side are actually classified as a metal, even including helium, or even including hydrogen, rather, is included in the metal groups. Kind of an odd thing to think about, but it's classified that way because we really don't have anything else in there. Intermediates carbon, silicon, germanium. These are things that are sort of metal-like character, but not exactly. They have kind of a hybrid of behaviors because they are somewhere in the middle where they can either become donors or acceptors depending on a number of external factors. So then getting to the last three here, 6A is where you've got, they want to accept 2 electrons to be closest to the inert gases. Then you've got 7A that wants to accept 1, and then you've got the inert gases that are stable and don't like reacting with any other species because they have no need to fill the electrons. They've already got what they need. So those are also the more electronegative elements to the right side. The electropositive elements are to the left side. So more electronegative tends to be the acceptor of those ions. They tend to be charged. The more electropositive are also highly charged. So everything in the middle behaves differently. Electronegativity ranges from about 0.9 to 4.1. So larger electronegativity. The 4.1 is fluorine, so that's by far the most electronegative, meaning when we make vinyls, for instance, PVC, polyvinyl chloride, means we substitute a lot of those hydrogens for these chlorine atoms. These are relevant because of the kind of character that they give the materials. So the polyvinyl chlorides tend to be strong and stiff. They tend to be fairly inert once you've already reacted these compounds that are highly different in electronegativity. The chlorine really doesn't want to react very strongly once it's already bonded in those polymers, but there are also fluorinated polymers. So if you've ever been through a hardware store, home improvement store, and you've seen black plastic for garden use, and you wondered, well, why doesn't that like biodegrade or something? Why doesn't that degrade out in the UV environment of the sunlight? Like, shouldn't that break down some of those chemical bonds? Because I know all of you have asked questions like that when you're walking through a hardware store. The reasoning is, especially for those black plastic fittings, a lot of those are not, in fact, polyethylene. They're often what's called PVDF, polydivinyl fluoride, meaning instead of chlorines on a lot of those, we add fluorine. And the fluorinated polymers tend to be highly UV resistant because when fluorine reacts with stuff, like, that's it, it's done. This is part of the reason why the most dangerous acid is in fact not hydrochloric acid. That is, while aggressive and dangerous, nothing like the acidity, the actual acidity of hydrogen fluoride. HF is an exceptionally dangerous material, extremely corrosive because it's the highest electronegativity difference of the acids. So fluorine reacts very, very aggressively, and that's why fluoride and things like that are used in toothpastes. Fluorine tends to be extremely aggressive toward anything biological and is more than happy to attack some of the carbon bases. So that electronegativity difference is very, very important. And that's why the bigger the electronegativity difference, the higher tendency there is to acquire electrons. So fluorine will happily rip them out of any other atom's hands and do what it's going to do. So fluorine is the bully out of the periodic table. So it has to be used very cautiously. But because of that, it's also very unwilling to give up those electrons when a UV ray strays and bounces into it. So even In the case of some of the maintenance protocols for the rubber seals for very expensive German convertibles and things, they have a seal dressing that you have to apply with a certain maintenance interval in order to preserve the rubber against UV damage. Of course, American buyers, like, that's not even a thing that they would ever think about. But there is an oil that is a highly fluorinated oil that they use in order to prevent UV damage to the underlying seals, preserving their lifetime. It's clever. It's also very expensive, but everything German is expensive. So there's that. Also always broken, strangely. So, maybe all that effort is for naught. Ionic bonds are important specifically for metals because that is a metal and a non-metal. So the metal donates electrons, the non-metal accepts the electrons. Going back to this, so we have a metal and a non-metal. So the non-metal on the right, and we have a metal on the left. So we have dissimilar electronegativities for something like magnesium oxide. Similarly, manganese oxide and any other oxide, iron oxide, same sort of concept, dissimilar electronegativities. So the magnesium is a 1s2, 2s2, 2p6, 3s2. The 3s2 gets donated, in essence, to the 2p4 of the oxygen, bringing the oxygen effectively to a 2p6, making both atoms equivalent and kind of balancing out their differences in electronegativity. So there's some examples. So that 3s2, there's a so those electrons are the donated pair, leaving Mg2 plus O2 minus. That charged interaction leaves an ionic bond, and this is where we have neutral electron set. So ionic bonding is different because it's trying to balance out these positive and negative ions for all of these cases. It necessitates electron transfer to have happened for that bond to work. And there is a large difference in electronegativity. So an example for a lot of instances, or a good one, is sodium chloride. Sodium being the metal in an unstable natural state. The sodium cation is more stable electronically. And the chlorine anion that sucks up the electrons is more stable in its state. So two unstable elements come together to form something as benign as table salt. Meanwhile, if you were to use pure sodium metal and it were to react with water, even in the environment, it reacts explosively, catches fire. Chlorine by itself is a native form, a gas that is poisonous. So those two poisonous and dangerous substances come together to form something as benign as salt. Just a very, very important thing to highlight why the bonding of atoms together becomes so important and why we need to understand it to understand the behavior of materials. So for ionic bonding, there's an energy minimum. They have to overcome an initial repulsion, and there has to be a balance of the attractive and repulsive terms such that the net energy is the difference. It's the sum of the two together, meaning the attraction divided by that distance plus the repulsion term, the repulsion constant at that point, at that distance, Rn. As the barrier gets overcome as they get closer and closer together, there becomes a neutral point at some point in terms of the potential energy. That neutral point, the difference between the neutral point and the attractive energy where that meets and this net energy comes together, that E naught is actually your binding energy. So we talked about that a little bit. And that happens at a specific interatomic separation. So you have to get them close enough together to overcome the repulsive energies and then reach this energy of bonding in order for that to happen. So that's why that net energy curve is so important. So ionic bonding is predominantly something that's seen in ceramics. And the way that that works is you have the side that's giving up electrons and you have the side that's acquiring electrons. So NaCl here is the difference between 1 and 2.9. MgO is the difference between 1.3 and 3.5. So this is why oxygen is an oxidizer. It is something that wants to oxidize, meaning it wants to take up electrons so that it can be closer to the behavior of neon. Calcium fluoride, CaF2, difference between 1.1 and 4.1. Cesium chloride, difference between 0.09 and 2.9. So there's a lot of examples of those kinds of pairings and those kinds of salts. The electronegativity is the sharing of electrons in the covalent bond. This is more reasonable and rational than some of the ionic bonding, where you have ions and radicals and all sorts of other behaviors. Hydrogen is a good example of that. So they each want to get rid of an electron to be neutral, but then together they can exist happily because there's two valence electrons. So each one is trying to sort of get rid of one and let the other have it. And so they just sort of keep playing hot potato, and I guess they're content doing that. So the electronegativities are the same. And this is determined by the valence behavior entirely. So it's the valence S and P orbitals that dominate what kind of bond character these will have. So in this case, it's just one, and it needs one more, and they have the same electronegativity. Bond hybridization happens where carbon, for instance, forms sp3 hybrid orbitals. So one of the 2s electrons gets promoted to a 2p. So this promotion of electrons, when the energy is raised, so as these molecules are coming together because of higher kinetic energy, there is sp3 hybridization, meaning that the 2s and 2p kind of group together, and we refer to them as an sp3. They become kind of indistinguishable as this bond promotion happens. So these are a hybrid orbital, and this is what we refer to as an sp3 orbital, leaving 4 of them looking to react and have other bonds. And this is the behavior that gives us our tetragonal shape, meaning it has 4 points. So it makes sort of like a almost like a pyramid, but it only has 3 sides kind of thing. So that's the geometry. The separation of bond angles is 109.5 for these sp3 orbitals. This is where the hydrogens are going to be positioned. If they're all hydrogens or they're all the same atom that they're being bonded to, if it's other carbons or if they're bonding to iron or whatever they're bonding to, so long as there's 4 of them and they are similar atoms, it will be at those same 109.5 angles. And that's where this comes into play because it's got 4 of those valence electrons in that hybridized sp3 orbital, and it needs 4 more bonds in order to fill that valence shell and reach molecular contentment. So the electronegativities of carbon and hydrogen are comparable so that the electrons are shared in covalent bonds. And that becomes very, very important. So the primary bonding, metallic bonding, is delocalized, and we represent it as something called an electron cloud. And there's an ionic covalent mixed bonding that can happen. So there's such a thing as a percent of ionic character. We'll spend a lot of time on, or a little bit more time on the metallic bonding, but just know that the ionic covalent sort of hybridized bonding does exist as well. So there's a percentage of ionic character that can happen. So this is especially true if things are largely different in electronegativities, and that's what these Pauling electronegativities are called. So we won't necessarily, at least I don't think, see those on an exam, but that'll be up to Dr. Wright ultimately. The percent of ionic character is something that generally she's not going to spend a ton of time on, but I wanted you guys to be aware that it's a thing. Secondary bonding happens between 2 of these atoms coming together. So this is what causes what are called dipole interactions. So there's fluctuating dipoles. You have asymmetrical electron clouds where you have more concentration on one side than another. This is a thing that we know from statistics can occur. When those 2 things happen, there's a temporary localized attraction between those electron clouds. Like liquid hydrogen, there's 2 H2s together, and there can be both of the electrons are all the way on the left side of one hydrogen and all the way on the right side of another hydrogen, and they have a sort of difference in charge that causes a secondary bonding. There's also permanent dipoles where, especially for ions such as hydrogen chloride, are good examples. There's secondary bonding between the hydrogen and the chlorine. Even though the hydrogen and the chlorine are already bonded, there's some additional interaction there. So polymers also have this secondary bonding between the hydrogens of the chains. Can happen. So it's not necessarily bonding between the hydrogens together, but the hydrogens, and they can have a slight difference in charge across that electron cloud with a little bit of asymmetry, creating some additional bonding interactions. And all of those bonding interactions of all of those levels have to be overcome in order for a reaction to take place. So this is why that's important. Especially when we get to deal with things like corrosion later in the semester. So the bond energy for ionic is very large, but the ionic is non-directional. So ceramics are very much uniform. They are symmetrical in a lot of physical properties. As a result of that, as well as electrical properties and thermal properties, metals are a little bit different. So we'll get to those. Covalently bonded materials have variable bond energies. So something that has extremely high covalent is like a large bonding energy is in diamond. Very hard to break those bonds. Possible, but difficult. Again, a lot of heat and pressure there. Small binding energies, bismuth. This is why bismuth salts are so readily reactive, is they're not strongly bonded. Covalent is directional. So there are some ceramics that fall in this category. Semiconductors and polymer chains. So very large percentage of things that you're going to deal with are going to be covalent bonding. In this class, however, there's going to be a large percentage that we're dealing with that are metallic bonding in nature. So those are, again, variable bond energies. So something like tungsten has a very large bond energy. Something like mercury has a very small bond energy. So that's why mercury can be found in a liquid state at room temperature, where tungsten, that's not going to happen. Tungsten, you can really apply an awful lot of heat to, and it will not degrade. It lights up very well, and so that's why we make filaments for light bulbs and things out of tungsten. Is a very fine wire that can be heated to a very high, by a very large current, and can remain in operation under those conditions. So non-directional bonding. Metallic is truly the opposite of directional bonding. Secondary bonding is the smallest of the bonding energies. It is only directional, and it's between chains or between molecules. So that gives you kind of a summary there. The properties from bonding give us information about the melting temperature. So some of you wondered, like, why are we attending chemistry class all over again? There's a purpose, because we need to understand the length of the bonds, the bond energy, and what effects that has on the melting temperature. So bond length just tells us the distance between the two bonds. That varies as the kinetic energy varies. That's what you see here. So the energy in the unstretched length is lower than the energy, the bond energy, meaning how much energy it takes to cause it to react. As you stretch and stretch and stretch those bonds farther apart, that bonding energy becomes less and less and less and less. It becomes less and less stable and becomes more and more reactive the harder you stretch those bonds. So it makes sense. The farther away they are, the easier it would be to interrupt that sharing of electrons, and for that atom to be reactive with another species nearby. So the melting temperature, as a function of energy, again, has to do with separation. So graphed on the same graph as the energy graph, the energy is in blue, the melting temp is in black. So the melting temp gets to be lower and lower and lower and lower and lower when they are at their unstretched length. The melting temp becomes much higher as you increase, or becomes less rather. So the zero is meant to be, the neutral axis there is meant to be zero for melting temp. So the magnitude of melting temp is greatest at the unstretched bond length. If you compress them together, the melting temp becomes lower because you're already storing more energy in the molecule itself. Same deal with bond stretching. You are physically storing more energy, so you need less temperature in order for it to cause a reaction. So by stretching the bond, you are physically storing energy, almost like a spring. It's the exact same mechanic, only it's storing the kinetic energy of the molecule in the physical length of the bond. So there's a lot of implications there. I'm going to restate that because I want it to land and make an impression. The bonds themselves are actually storing the kinetic energy of the molecules like a spring, and that's what changes how the melting temperature is going to be and whether or not the bonding energy is larger or smaller, because you're storing energy in all these different forms in the molecule. How fast is it moving? And that kinetic energy ends up being stored in how hard are the bonds being stretched or compressed. Usually the bonds are being stretched. So higher temperature is not required for melting if it's already under other kinds of interactions like that. So the properties. This causes also the same mechanic for thermal expansion. Because you add heat to the material, The material is the atoms are technically moving around more vigorously, but the way that this gets experienced by us at the macro scale is you heat a piece of metal and it changes length. That change in length at the higher temperature tells us something about the thermal expansion coefficient. Awesome. It tells you something about the thermal expansion and that behavior of the materials. So we have multiple contributors to that. And this is what it does. As you add energy into the system, you stretch out those bonds because the energy has to go somewhere and it has to store, literally like a spring, in those bonds. So we get a coefficient of thermal expansion. Some things expand significantly with heat, other things don't. So ceramic materials typically don't change size very much, so they have a low coefficient of thermal expansion. Things like wood don't change extremely, but they do have a coefficient of thermal expansion. So if you were trying to keep the inside of your house at 63 degrees and the outside of your house were at 65 million degrees, like is common in Phoenix, you would have a difference in thermal expansion between your roof and the walls that your roof are sitting on, because the walls would not be as stressed from the inside to expand, but your roof trusses would be highly stressed to stretch and expand. So those two things would fight each other. And what that does, all the way from the molecular level to the macro scale of your house or your dorm or whatever, is you experience that as creaking in the house. It's not actually because it's an old rundown house. It's just because you have fighting mechanics all the way down at the molecular level, causing all sorts of headache. So lots of fun and excitement that causes. So the coefficient of thermal expansion are symmetrical at a lot of different points, and that becomes very, very important for a range of reasons. So there is a smaller or larger thermal coefficient expansion depending on what the actual bonding energy is. So that creates all sorts of fun and excitement. So the ceramics are going to fall typically in the ionic and covalent bonding. They're going to have large bonding energy, so large melting temperatures, large energy levels, small alpha. So a small coefficient of thermal expansion. Metals varies a lot. They have moderate melting temperatures, moderate bonding energies, and moderate coefficients of thermal expansion. Polymers typically have very large coefficients of thermal expansion. They have typically very, very long chains, and so if you increase a long chain, each chain length by 10%, you're going to get a very large change in the size. So this is why we use polymers sometimes in between other things in order to absorb the expansion. So so that solid objects that are more ceramic-like, concrete is a little bit more ceramic-like than it is metal-like. Concrete doesn't do lots of thermal expansion. It's fairly small, but it does enough that you have to have some sort of buffer in between sections of something like a large bridge. Otherwise, large bridges would be destroying themselves all the time when the sun came out and fully heated them. So the polymers are primarily covalent and secondary bonding. Metals are almost exclusively metallic bonding. They can do covalent as well, but we're mostly going to focus on metallic bonding. So that will give you guys kind of a reasonable starting point for this particular chapter. That gets you into a little bit of no, I don't want I don't want those. Okay. So it's a little bit, so yes, there will be recordings. So there will be a couple things that are there, and yeah, there's going to be posting for the recordings. It takes a little while for those to get encoded, but I've also taught 340 classes in the past, so I'm adding these into those lectures because it'll make life easier to pull those all together. So you guys are welcome to take a look at those further. The idea is trying to make sure that when I've got them available, I'll get them posted. Right now, I'm going to go work on the next steps for me, which are going to be trying to make sure that like some of the initial due dates get updated. I'm not going to bother going through the whole semester because that's both impractical and unwise use of time at this point. There's probably going to be a large variance very shortly. So let's see. Let's see what you guys come up with. Any other questions as we go to close out for today?
So you'll be moving back the homework to Sunday?
Yeah, I'm gonna have to push that back into next week. So I'll probably do something like Wednesday or so. So there's a bunch of other mess that I have to deal with in terms of due dates and some of those things. So yeah, I'll be making some adjustments there.
All right, thank you.
The homework, no, for now, don't submit screenshots into Halo. I will get stuff transferred over from Wiley. Again, this is not normally representative of how things are done at GCU. This just happens to be a special peach of a semester. So grace on both sides of the equation is a wise mechanism through which to move forward. So some of that could change when Dr. Wright comes back, especially in regards to things like late assignments. But I'll make sure that these first due dates are pushed back a little bit so that we can slightly unmess the mess here. Okay, other questions? And yes, I think there are lecture notes in Wiley that are available. So I believe that's accessible to you. Those will probably be a little bit more detailed than anything that gets posted. But again, recordings will get posted once they're done rendering. All right. Any other questions for now? Okay. If not, then you guys are good to go, and I will see you next week. Take care, all.